Hello, everyone. So today we're going to go ahead and talk about something very, I guess it was a really hard topic in class today, or not today, on Thursday last week. Um, it was basically about stoichiometry, starting out with chemical reactions. Understandably, it's a very difficult topic, so let's go. I'm just going to make a video on it. Quick warning: this is a very long video, so if your intention is to watch a quick video, then go find a video from somewhere else that's not specialized to your lecture. Basically, I'm going to go over as much of the lecture as I can. This is not a substitute for your reading, so please read. But if this is something where you want to find an answer to one of your homework questions, which I did this specifically, I'm making this right after the homework because I want you guys to be able to learn from your mistakes, and you have to mess up to learn, basically. Um, if you're looking for something that's just giving you answers, this is not the video for you, and basically, I'm not the right preceptor for you because I'm not the one who gives you answers, I teach you. So anyway, with that aside, let's go ahead and be cheerful. And let's start. So chemical reactions, basically, just think of them as recipes. I'm going to use this comparison a lot, but recipes. So I'm going to give a good example here of a chemical reaction, and you guys saw it in class on Thursday, and that is 2SO2 plus, and this is a gas, plus O2, so oxygen gas, yields 2SO3. So basically, the way these chemical reactions work is these are known as your reactants. Reactants. And then, I hope I spelled that right. Yeah, I did. And then these are your products. Products. So a lot of the times we'll say for reactants, sometimes we use the word starting material, or SM as your starting material. Starting. Oops. Material. And a lot of people like to end, so like products, I prefer the word products. A lot of people prefer the word end product or ending result. No, they're products. And I'll normally, in certain videos, if I make any more, I will label this. I'll either use SM for product, or for reactants, or PTD, which is product. Hopefully that makes sense. So, reactants and products, normally starting material is something that we transition from saying reactants to more starting materials during organic chemistry, because you normally have an organic material as well as an inorganic material. So, for example, something like ethanol, or ethanol, sorry, if you're not from England. Alcohol, right? CH2 or CH3, CH2OH. That's an organic material, and we can use something like sulfuric acid. Well, bad example. Let's use table salt, NaCl. That's not organic. So that's why we say starting materials, but for now you can just say reactants. That's perfectly fine. Basically, this little arrow just means that the reaction is basically you're going from this stuff to you're going to this. And this is what we want, basically. Um, in easier words, I can actually say that. So basically, this is another way of saying. I'm trying to find out how to say this without confusing you guys. Okay, so two molecules of SO2, gaseous SO2. So two molecules. We'll go over the word molecule and mole a couple minutes later, but two SO2s plus one O2 yields 2SO3. Basically, it's giving you the recipe for this reaction. It's just like opening a cookbook and you saying, oh, okay, a chocolate cake. I'm sorry, guys, I'm really hungry, so if I make you hungry, forgive me. Yeah, let's say it's for chocolate cake. It tells you, okay, use this much chocolate, this much flour, these many eggs, oil, water, sugar, whatever. basically this is the same thing except for chemicals, because chemical reactions are important for us to do chemistry without dying or blowing up, because that could like happens to many of the older chemists, the ones who are now dead, who like discovered chemistry, or not discovered chemistry, like explained the rules and everything. Basically, some of them died because of explosions, or they burned their arms, blah blah blah, etc. etc. So basically, that's what a chemical reaction is. That's really it. There's nothing really to it. If you guys have trouble following me in this video, do know I'm actually going through the full notes. I have a different monitor up with the full notes. So I'm not just throwing information out there. It exists on the full notes. If you don't know what that is, come see me. We need to talk. Like, seriously. Okay, so basically we ask ourselves, well, okay, in a lab, or actually in a kitchen, when we measure stuff out, like let's say sugar, we normally have like a measuring cup, right? Measuring cup that has like these little things, and they have horrendous units called cups. I hate these. I hate these. I hate these. I hate these. I cannot stand them. If you guys don't know, I'm from the UK. I am accustomed to knowing grams, kilometers, not inches, but centimeters, Celsius. That's what I know. So cups to me, horrendous, awful, awful, awful. However, they're there for cooking, and it's very easy to use because most Americans, actually most all Americans, know about cups. So they can be like, oh, okay, they can estimate what a cup is. But in science, how do we actually determine the amount of something? Like if I asked you, give me, 7 grams of NaCl, which is not a lot, you'd have to use a balance. Right? Ooh, nope, I'm going to draw it a little better. Nope, I'm going to draw a little better. And there's like a little, so there's a balance, there's a little disc inside, and there's like a number reader. Sorry, my drawings are awful. I'm also using an iPad, so, that kind of happens. Use a scale, and a scale is not weighing a product. You're actually massing the product, or reactant, whatever. Like the I guess chemical or a compound you're using, you're actually massing it. You're determining how much of it is on this scale, versus something like the horrendous units, pounds. This is something else. If you take a physics class, you'll learn about this. Pounds is about how much you are in terms of like weight. Weight is not mass, basically, is what I'm trying to say. Because basically, a mass of 7 grams will be the same here or on Jupiter or on Mars. Pounds is not the same thing. I mean, cups is also, but this is the U.S. customary system. I hate. Metric system, beautiful. Every scientist uses this. And pounds is not mass. Just that's all I want to make sure you guys know. But the really important thing is, how do you know like mass versus say number of particles? Like 7 grams. Okay, well, how many particles are in 7 grams of sodium chloride? Well, basically there's a little bit of a problem here. Some scientists were talking and they were like, wait, there's no actual way of figuring out, how much something is equivalent to something else. There's no, like, there's grams, there's kilograms, milligrams. There's not really anything that can basically identify everything in the chemistry world. For example, we have the US dollar here. We have, the British pound, the euro, where everyone else uses Canadian dollar, Mexican euro, Mexican, what's it called? Pesos. Australian dollar. I don't know currency. The Japanese yen. That one I know. So basically, there's no like identifying factor. You have to convert things, and it's kind of annoying. There needs to be a universal item. What is the universal item? For chemistry, there is such a thing. For the world, if there was some universal currency, well, actually it's gold, technically. Gold is a universal currency. It's valued all over the world. My American dollar is not valued in Japan. I guarantee you that they're not going to give a shit about give a crap about my dollar in Japan. Same thing, same difference here. No one cares about how many grams of anything you have. They care about the moles. That's the universal currency here. Moles. Beautiful, 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 beautiful. You will use it everywhere in terms of chemistry. I use it in my labs to this day. I will not lie to you. I use it, I use it, I use it. I could show you my lab notebook. Do not tell me I'm not going to use this as a nurse or whatever the hell you want to be. That's a lie. That's a straight up lie. Sorry, before I get really freaked out. Basically, the mole is a number. It is a conversion factor that assists us in trying to identify, okay, you have something moles of sodium chloride versus another amount of moles of sucrose. Basically, these two are very different compounds. So having moles helps us identify, okay, well, I know that, so moles, okay, let's go with this. Moles is a universal currency of measurement in chemistry. So when we see recipe books with, our cookbooks, we see all sorts of measurements, ounces, which are, I don't even know, what is an ounce? Please, someone explain this to me. Oh, in the comments, please explain what an ounce is to me, because I don't goddamn know. I use the milliliters. You guys. Sorry, I could go on and on about that. Recipe books, you have cups, ounces. Some have pounds, like half a pound of sugar, which is outrageous. Quarts? Yeah, everyone used quarts as well. Cannot stand you guys. And there was like the one recipe thing where, and then of course, like 2 eggs, There are units everywhere. There's no one solid thing. Okay, well, I can, like, basically you have to have a measurement drawer that has like cups, teaspoons, tablespoons, little cups that measure ounces, and like a little scale for like pounds. No. For chemistry, you have a gram, you have a mass for grams, and then you have, or milligrams, depending on how little you want to go, and then you convert it to moles. And moles basically helps identify your recipe. All your recipes or chemical reactions for chemistry are used in moles, nothing else. Super simple. No need for all the, crazy stuff in the kitchen, like cups and ounces and etc. Moles is pretty easy. And the guy who came up with this number, he actually didn't even know he came up with this number. He died before this happened. Isn't that kind of sad? You, become famous after you're dead. You don't even get to enjoy it. That would make me very, 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 very horrified. So, if the guy is a ghost, I'm sorry. I feel for you, man. His name is Avogadro. He's a very stern-looking man. Avogadro. I was about to write avocado. That's when you know it's time to go sleep. Avogadro's number. Sorry, I'm lazy. I'm not going to write the word number. Basically, this, on a chemical or on an equation sheet, if there was one given to you, you would see this. Number, nope, that's wrong. I'm going to use it a little better. There we go. Number, subscript, Avogadro. And that's just Avogadro's number. And this number is actually 6.02. Your PowerPoint says 022, so I'm going to go with that, times 10 to the 23rd. Side note, guys, on your calculator, do not type in times 10. That is horrible. Calculators have this new little amazing function called EE. This thing basically means, oh, you mean times 10. Basically is what the calculator thinks. So when you type into a calculator, you should be typing in this, 6.022E. It should look, I think it looks like that, right? Yeah, it'll look like a single E. The button looks like EE. That's what the button looks like, but it'll come up as 1E, 23. You're basically saying 6.02 times 10 to the 23rd power. Done. If you don't know what that is yet, again, come see me. We need to talk. But basically, 6.022 times 10 to the 23rd, very important number, just like the speed of light for physics. You have to know it. You have to memorize it. Love it. Forever. That's Avogadro's number. You'll use it all the time. And basically, it's a way of finding the number of molecules / particles of any 1 mole of substance. So basically, if I had exactly 1 mole of anything in the world, say 1 mole of freaking pennies, I would have basically this number. Whoops, that's erasing. That's bad. This number, I can't circle today, that number of freaking pennies. So 1 mole equals that number. So if I had 1 mole of cookies, 1 mole equals 6.022 times 10 to the 23rd. stuttering. Sorry guys, it's really late at night. If I start to entertain you, laugh at me, but please don't be rude. But yeah, 1 mole equals that number. So basically, if you have, like, let's say half a mole, then it's going to be that 6.022 times 10 to the 23rd divided by 2. That's literally it. There's nothing else to it. Do not freak out at how hard this is. It's not that hard. But yeah, that's really it. So really helpful things to know is that a mole equals that number, 6.022 times 10 to the 23rd. That's the number of particles, molecules, atoms, things, anything. If you have 1 mole of it, it's that number in terms of amount, quantity. So if I had 1 mole of oxygen, that's how many oxygen particles or molecules of oxygen that are in the air. If I have 1 mole of dust, Jesus, that would suck. That's how much dust I have, which, my God, please leave that area. You will die of allergies if you're like me, who just suffocates at the sight of dust. We did some stuff in class about 1 mole of pennies, how many how much money would each person receive in the U.S. I'm not going to go through that. You can look at the slides if you're interested in that. However, next topic is AMU, or atomic mass. You've seen this before. This is not new. However, we're going to go ahead and talk about molar masses. We're going to basically talk about how to calculate this. So let me scroll down here a little bit. Okay, so a molar mass of anything, when you have, like, in the periodic table, actually, let me just pull up a, why am I drawing a table? Periodic table, perfect, like that. Table, there we go, table, haha. Okay, sorry, my display is a little laggy. Let's look at iron. It's like in the middle of your screen, number 26, iron, which is spelled wrong. We say it differently. It's iron. LOL. Okay, iron. So this is the atomic number. We know that from exam 1. This right here is what I'm looking for. 55.845. That's an important number. If I ask you to calculate a molar mass of iron, that's the number. You just write that down and done. But it's not that simple. So basically, all this is, okay, let me give you a small thing, like CO2. CO2. And I ask you, calculate the molar mass, or molecular weight, however you want to call it, of CO2. Well, what do? Well, you look at the periodic table and go, okay, well, I have 1 carbon atom in this molecule of CO2, just by definition of C1O2, right? So that's 12.011. So we have this number times, well, O is 15.9999, or just 16 for funsies. Well, I have 2 oxygens, so I'm going to basically have 12.011 plus 16 plus another 16. Or you could honestly just do 16 times 2 if you're really smart at math and like math. No, this is easier. 16 plus 16, whatever. That's your molar mass. Whatever number you get out of that on a calculator, that's your molar mass of CO2. We use this to basically go from grams to moles. So if I say, and we'll talk about this later in class, maybe in this video, who knows, if I scroll down enough. In really high, high critical calculations, you'll have to go from a certain number of moles. Like I could say I have, let's say, 18 moles of CO2. How many grams of CO2 do I have? Well, you'd have to use the molar mass to figure that out, because basically a molar mass, if I remember correctly, a molar mass unit is grams per mole. Just from the unit itself, you know that a molar mass, with the unit grams per mole, has something to do with grams and something to do with moles, which is a good indication that I could use it to convert from grams to mole. Wow, crazy. Just like miles per hour, I can convert from hours to miles and miles to hours. Same exact thing here. You're just adding another conversion factor, which these are more fun than the other crap that we've given you thus far. Basically, if you don't remember how to do conversions, this is going to suck. So come see me. I'll help you. So that it won't suck. Because basically, this is the most fun I ever had in chemistry. This was the most fun. Because the amount of demos that my class did. Whew, demos were so much fun. But basically, you had your turn. You had your turn in your lecture. That was like, what is the mass of 1 mole of carbon dioxide? And you were basically asked to figure out what a mole of carbon dioxide was, which in this case, it's, well, this number right here, 44.01 grams. Actually, I haven't written this number out, have I? Let's use red so you can see it. 44.01 grams is 1 mole. I figured this out by saying, okay, well, 1 mole times this number. Now, don't worry about the math to this yet, but 1 mole basically equals the molar mass of this stuff. So if I said half a mole of CO2, it'd be this number divided by 2. Just try grasping that kind of conversion stuff for now. Then we had a very interesting thing in the lecture, which honestly none of you guys did. So I took a snapshot of it, and we're going to do it right the hell now, because I got really mad that no one did this in class. Literally freaked me out. So let's do it. Can I write? Yes, I can. So this question was saying, okay, well, draw reactants and write a balanced chemical equation. Now, a lot of you didn't do it because you guys are terrified. No, don't do that. Freaks me out. Freaks everyone out in terms of preceptors. Some of them will let you get away with it. No, do not do that. That's how you fail classes. Anyway, happy J over here. So we know that purple is X and blue is Y. Just, that's what that says, in case you think I'm making stuff up. Basically, we're just going to say, okay, well, I know that I get some abomination of things here. What did I have beforehand? And I give you a hint. Basically, it says, they look like this. Just count how many of them there are. That's literally it. So the way I do this is, okay, well, let's actually, let's go ahead and erase this. Let's go ahead and just count the number of particles I have, or molecules I have here, or atoms even. So, again, purple is X, so I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Yeah, 12. 12X. 12X. And let's count how many Y's we have. 1, 2, 3, 4, 5, 6. Well, we have 6 Y's. Okay, well, basically over here, my X's and Y's are going to be XX and YY. Right? It's going to be an X bonded to an X and a Y bonded to Y bonded to a Y and an X bonded to an X, basically. There's no other type of, molecule here. There's no other reactants. So, okay, well, I have 12 X's, and if each X is bonded to each other, well, that can give me, oh, look, 6 X's. So let's go ahead and do it. I'm going to go ahead and write these out. Actually, I'm just going to go ahead and use dots. So, purple dots. Nope, that failed so badly. I'm going to draw them out then. There's 1. I think that's 1. It'll show up in a minute, guys. There we go. 6. Right? That's literally all you had to draw. And then, actually, no, that's wrong. Oops. I made a whoopsie. So, yeah, that's 6 atoms. We have to draw 3 more. So let's go and do that. There we go. That's better. So we have 12 X's, but they're bonded to each other as basically a diatomic. As I'm not making this up. There's no way that I know this besides the fact that it's given to me right the hell there. Okay, this is not hard, guys. And then, okay, I have 6 Y. I counted 6 Y's over here. I'm going to use blue. 6 Y's over here. Okay, well, again, each Y is bonded to itself to get, like, a YY or a Y2. Who knew? Well, there's 6 atoms of Y. If they're each bonded to each other, that's only 3 of them, right? So 3 molecules of YY, or Y2. Done. That wasn't so hard. That's literally your answer. Now it says write a balanced chemical equation. Well, we can honestly, so balancing it, I do afterwards. My choice is honestly to write out what I know and then fix it from there. So let's do that. Well, I have 6 x2s, right? So I have 6 x2, because x2 is the x is bonded to itself, plus, well, I have 3 y2, right? And this yields, through the chemical reaction, it yields, well, 4 of these little things that are basically x3y, and then, well, there's some extra stuff going on. The reason why I'm not going to include this in here, the reason why I'm not including it in there is because look at what we have beforehand. This is also YY. This means that this is not a product, it's just left over. So nothing happened with that. It's not a product, it's just still there. So I'm not going to write it out there. This is my chemical reaction right here, but it's not really balanced yet. And I'll explain why. So basically the idea around this is you kind of have to simplify. So let's go ahead and do that. So the simplified answer to this is basically going to be 3 over here, just y2 there, and this will become a 2. If you don't understand how this works, please come see us. The reason why we simplify is because this chemical reaction will ensure that we do not have any extras. And that's what we want. We want to make sure we can maximize product without wasting stuff. So, okay, let's go to the next topic. Conservation of mass. Okay, so I'm going to go ahead and remove this thing from the screen. So conservation of mass is basically where, okay, let's say you have, I don't know, gunpowder, right? You have gunpowder in a little dish, gunpowder. And you have a closed container, right? Very closed. You have a little igniter that when you press a button, it will light the gunpowder. When you light the gunpowder, it makes some smoke. Hooray, it burns. This is gone. It's now smoke everywhere here. Basically, oh, there you go. Now you can see the smoke. Basically what happened after we ignited this gunpowder is, let's say I had, 2 grams of gunpowder. Sorry, that looks weird. No, let's fix it. Gunpowder, like that. There we go. Basically, when we ignited this, the gunpowder is gone. However, the smoke that is still there, some of it's CO2, some of it's other stuff, it's still there. Right? Like, it hasn't gone away. We haven't destroyed matter. That's not possible without using something called antimatter. Take physics if you want to know what that is. That there's no such thing as getting rid of matter. There's no such thing as making matter out of nothing. Basically, during the Big Bang, everything that exists in the universe existed as soon as the Big Bang happened. Nothing else was created, is basically what we're going with. So conservation of mass simply says that, yeah, the 2 grams of gunpowder we ignited, 2 grams of something, or not really 2 grams, it's something else is still there. The same amount in moles. So I don't really know the molar conversion of gunpowder. I should. However, let's go with, instead of 2 grams, let's go with 2 moles. If I had 2 moles, which is a crap ton of gunpowder, good lord. So I had 2 moles of gunpowder. Basically, 2 moles of something else is still in my box. There's, besides the air, 2 moles of some other product is still there. I've not gotten rid of anything. I've not made anything. I've just chemically reacted it and things happened. It's hard to really see that when you're burning things. When you're burning a piece of paper or you're burning, let's say, an omelet because you forgot it's there and you were doing your hair instead. Basically what happens when you burn something, yeah, you like there's an odor that you smell. That's part of the matter that was within that omelet or whatever you were doing. If you're burning your hair, particulates of hair, you're smelling that. There's a chemical reaction with your hair and the lava hot iron that you have on it, and it's burning. Basically, that matter, your hair is gone, yes, but that doesn't mean that what you had, or that doesn't mean that it's not anywhere else. It's not in the form of hair anymore. It's in the form of bad odor and other products that I don't know, but it's still there. So basically, if I burn zero point 0.2 moles, let's say I burn 0.2 moles of hair, right? I have hair and I burn it. Burn. These are my little heat waves. If I burn them, this 0.2 thing of hair, 0.2 moles of something, right? This is moles. 0.2 moles of something is still there. It's not hair, but it's something else. So that's all it is. Conservation of mass basically says that whatever you had before, you still have. It's just different. And you might not have the exact same grams of it, but somehow you still actually do. It's just in different shapes and sizes. And I like using moles, it's easier. And then we go into our favorite topic, stoichiometry. Stoichiometry. This is how I write things, is I word them out so weirdly. Basically, stoichiometry, all it is, when you have a cookbook open, someone else has done. So think about this. How is a cookbook made? How is a recipe created? Someone sat there and figured out the best way of making that chocolate cake. One evening they made it with too much flour and they got a really bad result. So they scrapped it and tried, less flour, more water, maybe more eggs. They went through a process of trial and error. I would assume trial and error because that's how you figure everything out in terms of cooking. They basically went through a trial and error concept to figure out the perfect ratio of flour, egg, water, chocolate, blah, 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 blah. Stoichiometry is the way that we go through. We don't want to sit there and mix 2 chemicals or 3 chemicals and have them explode or kill us with toxic gas. That's not how we want to do things. That's very unsafe, and basically we'd have no chemists in the world if that happened. And all our doctors would be dead. Another way, and nurses, so if you're a nurse, pay attention. Basically, another way is you calculate, you calculate, how many moles of this equals this, or how many grams of this will I get if I mix in something else. You basically do this to make your recipe and predict your products through math. And because we do it through math, we get what's called a theoretical number. And I'll talk to you why theoreticals and actual numbers are different. That's kind of a side note. Don't really worry about that too much. Just know about stoichiometry. So I'm going to give you an example. And that is, let's use methane. Yeah, methane. CH4 plus 2O2 yields CO2 plus 2H2O. Basically, I'm sitting here saying, okay, well, how many moles of CO2 and H2O are going to be made if I blow up 0.25 moles of ethane, or of methane gas? That's not right. That's a 4. Basically, you have to do some math to figure out, okay, well, yeah, there's a certain number that's going to be produced here. If I burn 0.25 moles of methane, you look at the chemical reaction and say, okay, well, I have 1 methane here. How many moles of CO2? Well, I have 1 mole of CO2 coming out. right? If the recipe basically tells you if you have 1 mole of CH4, you're going to have 1 mole of CO2 coming out. That's what this reaction tells you. So if you burn 0.25 moles of methane, you're going to come out with 0.25 moles of CO2. That's it. Now, a little different if you look at H2O. Why? Because there's a 2 here. The chemical reaction / recipe has told you that when you burn methane, CH4, you're going to result, 1 mole of CH4, you're going to result in actually 2 moles of H2O. That means I'm going to double in the number of moles of H2O. Not that I'm making water out of nothing. That's simply just saying when I burn methane, you're going to get 1 mole of methane, you're going to get 2 moles of H2O. So using that logic, if I burn 0.25 moles of methane, well, if 1 equals 2 here, if it's a 1 to 2 ratio, then this would have to be 0.25 times 2, or 0.50 moles of H2O. That's it. I'm not writing this down because I basically want you to listen, because if you don't listen to it, basically you're not paying attention. I'm not going to write stuff down because I want your undivided attention. And that's really it. The rest of the stuff is stoichiometry. We're going to go over in class if we haven't already done that. But I definitely want you guys to use this information for now. Let it sink, in for Monday, because it's like literally 11:57 in the evening here, so there's no way you're gonna watch this tonight. Watch it whenever. Or actually, you're watching it now. That's weird. Why am I saying that? Let this information sink. Right, basics to stoichiometry, basics to chemical reactions, and basics to stuff like limiting stuff, and how to basically write out a balanced chemical reaction or chemical equation. The hard stuff in terms of the math, we will go over in another video. So this will be stoichiometry part 1, parentheses basic, I guess. I don't know. I'll label it something. And then the second video will be the more difficult stuff. Definitely know that I can only do so much in terms of math on a computer with a YouTube video. You need to come into office hours as well if you don't understand something. But this is just a way of kind of helping you out here. But that's really it for tonight, guys. I'm going to go to bed. You guys should go to bed as well, or go study. I don't know, whenever you're watching this. Thanks for watching, everyone. I hope this was important, or hopefully this was helpful to you. I like making the videos, so I hope they really help. Tell your friends about them if they're helpful to you. If they're not helpful, tell me that I'm stupid. Whatever, just go for it. Again, thanks for watching. You guys have a great evening, day, morning, night. I don't know. Take care, guys.